The scheduled video I'm supposed to be doing right now is on rogue planets, followed by discussing rotating habitats and interstellar colonization. I've gotten quite delayed on those in large part because there is a common thread in all of those that really needs to be addressed first. And that's how we power these things. Running spaceships, powering artificial habitats or giant launch loops, or terraforming planets takes up a lot of energy, and that isn't something we have an abundance of these days. So if you're one of my regular subscribers, sorry, but this needs discussed first. If you're not one of my regular subscribers, and this is the first video you're watching, then you're probably noticing I sound a bit strange. That's my speech impediment. And you might want to turn on the closed captions, which is down near the subscribe button. Subtitles help, and even discounting the speech impediment, I do have to toss out a lot of more arcane technical terms in these videos that you might not be too familiar with. Also, if you're new to these videos, I will occasionally reference other videos, and that will typically be accompanied by a thumbnail on the screen with a yellow or white box around it. You can click those at any time and it will just pause this video and open that one in a new window. A common theme in a lot of these videos has been where you get the power to do all these neat things like throw up an orbital ring around your planet or terraform another planet. I like to discuss some of the ways this can be done without a revolutionary new power supply, but I tend to mention how useful nuclear fusion would be if we had that. I've never really gone into the details before now, though, and while there are a lot of videos out there discussing how nuclear fusion would work, they don't tend to really discuss the full weight of the sort of economic impact a functional fusion reactor would have. Fusion's also gotten a bit of a bad reputation as the technology that's 20 years away, and always will be, one not helped by a lot of overhyped alleged cold fusion inventions. People are dubious about it, weirdly more so than something like fast and light travel, which we outright tell people is scientifically impossible. So I like to explain how a lot of the ideas discussed on this channel can be done without it. Fusion is a huge game changer if you've got it, but it's not absolutely necessary for us to expand out into the stars, and I don't want people to think that all is lost if we don't have this cool piece of tech. Today we're going to skip over the skepticism. We're also going to skip over the mechanism for doing fusion. We've got a number of different reactor designs, all coming at fusion from different angles, and none work entirely yet, so detailing those, especially when there are videos that already discuss that, would seem pointless. I will explain the oldest known design real quick, the one that works and we've always known would work, just to dispel some of the skepticism. But before doing that, here's the 60-second overview of what nuclear fusion is, and how it differs from nuclear fission. Nuclear fusion, which is what powers the stars themselves, is the process of slamming together a lot of light elements like hydrogen, or hydrogen's main isotope deuterium, together until they form a heavier element like helium, or slamming helium together to make carbon. This process releases a lot of energy, because while deuterium is 1 neutron, proton, and electron each, and carbon is 6 neutrons, protons, and electrons each, 6 deuterium atoms weighs noticeably more than 1 carbon atom. All that missing mass was converted into other stuff, neutrinos and high-energy photons, and we can use those photons to make power. Fusion fuses together lighter elements into heavier elements and releases energy doing so. And it's a lot of energy, millions of times more energy than an equal weight of gasoline or coal or ethanol. Fission does it backwards, taking big, heavy elements like uranium and turning them into smaller ones, releasing energy while doing that. Fusion produces more energy than fission does, and there's a lot more hydrogen, deuterium, and helium out there in the universe than uranium, so it's a better power source. The problem with doing fusion is it requires incredible heat and pressure to make it work, which is hard to maintain in a lab without spending way more energy than you get out of the process, and it also wrecks your equipment. That's why cold fusion is always such an attractive idea, though it doesn't look to be in the cards. It's also why fusion bombs are durable, because you're creating one big immense blast and you don't care if your reactor is shredded to atomic dust in the process. And that brings up the one known form of man-made fusion we do have, the original one, the H-bomb or fusion bomb. This device is also the reason why we have the irritating quip about how fusion is the technology of the future and always will be. We went from a basic understanding of atoms to the fission bomb and the fission power plant in about 1 generation. We then got to the fusion bomb only 7 years after Hiroshima and Nagasaki. Some jumped the gun thinking we'd progress as fast and have fusion on the same timeline. That turned out not to be true, and scientists stopped saying it was soon ahead for some decades. Now they are saying it again. Fusion isn't a certainty, and I certainly won't say it's just 20 years off. But for my part, I'm very optimistic we'll crack the problem in the future, and I genuinely would not be surprised at this point if we did have commercial fusion reactors in 20 or 30 years. But I mentioned not just a working fusion bomb, but also a working fusion reactor that we've always had. And I don't mean the sun. Simply put, you can build a fusion reactor just by building yourself a very large, mile-wide, insulated and sturdy bunker full of water and with turbines on top. You then dump in a fusion bomb and let it go off. That heats the water, produces steam, turns the turbines, makes power. You dump another in when you're done, and that's it. And it's always been doable. You dump a multi-megaton nuclear device into a big, hardened, water-filled sphere a few miles across once every hour, and you've got all the power you need to run an entire, industrialized continent. This isn't really a terribly enticing way to go, though. H-bombs, even without the expensive rockets attached to them, aren't cheap, and a structure like that would make the Hoover Dam look like a Lego project. But I offer it as a known way to do fusion power. Let's assume we've got something smaller going. Forget the method, just assume we have one for the moment. There's still two types for our interest: compact and high-powered versions, and large low-powered versions. This isn't about efficiency, but power produced per kilogram of total reactor and fuel, and the breaking point where we're concerned would be whether or not you could make one powerful enough to lift itself and some payload into orbit. It's like a solar panel. Most solar panels can produce 1 billion or so joules per kilogram of their own mass per year, and live for a decade or so. Conservatively, that's 10 billion plus joules of energy per kilogram of panel. That's a few hundred times more energy per kilogram than gasoline or rocket fuel have. But it does that over a decade, and so you can't make a solar-powered launch vehicle. It just isn't powerful enough to get into space where you need to expend all that energy in a few minutes, not 10 years. Same is true for a nuclear fission plant. Of course, uranium produces way more power per kilogram than solar panel or fossil fuels, and it's still high even when you start adding in all that radiation shielding and power generation ability. A nuclear fission plant can't just fire out steam from the bottom and lift itself into orbit. A nuclear fusion reactor may or may not produce enough power, which is energy per unit time, to lift itself into orbit, even though it would easily produce far more energy over its lifetime than was necessary to get into orbit. I tend to refer to any hypothetical fusion reactor that could as a compact one. And if you've got one, hey, great. But if you don't, you still have options like space elevators and orbital rings and launch loops powered by fusion to get the job done of getting stuff off a planet. Once you're off planet, it doesn't matter if the fusion reactor or fusion drive is particularly powerful, since a very slow acceleration for hours and days is just as good as a fast acceleration that runs out of fuel in a couple minutes. That's why ion drives look like very nice things to have in space, but are useless for getting into orbit. They produce a lot higher final speed than a classic rocket, but take a long time to do it, so they could never get out of orbit. For interstellar travel, or even interplanetary travel, taking a long while to get up to and back down from your top speed isn't that big a deal. And if you're curious, the usual assumed speed for what we call a fusion torch drive is around 10% of light speed, the approximate maximum you could get up to if you need to carry your fuel to speed up and slow down. But we'll talk about that another day. What we need to look at now is what fusion actually does for an economy. First, while it isn't an infinite power supply, it is one that produces energy from the most common substances in the universe, and produces many millions of times more energy per gallon or pound than gasoline or coal. It takes several supertankers worth of oil to run the US economy every day, whereas one supertanker full of fusion fuel would run the US economy for several thousand years. That matters a lot when we're talking about some kind of deep space settlement too far from the sun to use solar power, because it means that even if they needed to import their fuel, rather than just sucking out of the local thin gas floating around, they could keep millions of years worth of supply to run their habitat in an area much smaller than the habitat. and in a bit we'll actually run some numbers to show how much energy, or weight in fusion fuel, be it normal hydrogen or deuterium, it would take to keep someone alive and comfortable for 1 century, a nice long human life, including the energy needed to grow their food. But let's talk about a more near-term effect. We know cheap electricity from nuclear fission, let alone fusion, is very handy, but it doesn't help much for cars. You can't build a fission reactor into a car. No, seriously, the thorium car is so much absolute bull. You can build batteries, but all batteries stink. Should they ever get much better than solar, becomes a much nicer option. But if they don't, and you've got fusion, then you've got all the gasoline you ever want, and without worrying about filling your atmosphere with carbon dioxide. Why is that? Well, fossil fuels and other hydrocarbons are great power supplies because when you expose them to oxygen at high temperatures, they burn and break from being a hydrocarbon into being water, hydro, and carbon dioxide while releasing heat energy. You can run this process backwards and cram the water and carbon dioxide back together to get hydrocarbons and oxygen back. This first process produces energy, and the second process sucks it up, and in truth sucks up a lot more energy to run backwards than you get out from burning it again. And there's no super science in doing this, it's easy old chemistry, it's just pointless right now. But if you have a basically infinite supply of power at your giant fusion reactor, who cares if it takes 1 billion joules of energy to produce 1 gallon of gas with its mere 130 million joules of energy? Your average AAA battery costs, say, around $1, not much less than a gallon of gas does, but contains not even 1/1000th of the energy in that gas, and way more energy is lost recharging a battery than stays inside it. But it's still worth it for its portability. If you've got cheap fusion, then you've got an unlimited supply of cheap hydrocarbon fuel and carbon-neutral fuel because you just make it by sucking carbon and water right back out of the air. Now, if you've got batteries that are more energy-dense than fossil fuels, you wouldn't bother, but we don't have those yet either, and batteries generally leak power too, way faster than a tank of gasoline does. Nor if you've got cheap fusion do you have cheap power and fuel only. You've also got cheap fertilizer. The nitrogen we use as our main fertilizer is mostly produced from ammonia produced by the Haber-Bosch process. With cheap electricity, you can electrolyze water for its hydrogen and suck nitrogen from the air to produce ammonia. We talked about this a lot in the terraforming video in terms of transmuting local substances into things we can breathe and drink. So you can make nitrogen fertilizer very cheap. Ditto for phosphorus, our other main fertilizer. You can get cheaper supplies of it. Phosphorus doesn't occur naturally in dense and easily mined chunks in many places, so it's expensive and scarce. But if you've got cheap energy, you can separate it from low-density supplies in a number of energy-expensive but simpler methods. Even something as low-tech as a centrifuge. And that applies to any mineral, even if you ignore that you could mine asteroids economically if you've got fusion. Recycling of almost anything becomes way cheaper and easier as well. Ditto water. We always have water shortages on a planet whose surface is more water than land, because it's all undrinkable salt water. But with cheap power, you can desalinate water cheap enough for agricultural purposes. You can't have a drought because you never run out of water, and you've got cheap power to irrigate fields with. You've got cheap, carbon-neutral plastics or polycarbon sheets to make greenhouses, which seriously cut water usage and keep warmer temperatures, but you can also heat them since you have cheap power. So you gain all the deserts and tundras as growing space, and more efficient growing space since greenhouses load up with warm temps and cheap fertilizer produce orders of magnitude more food than old-fashioned pre-industrial farming. But it doesn't end there. You've probably heard of vertical farming, the notion of growing food in multiple layers. Now this idea, outside of overhyped pop-sci articles, normally only calls for a couple layers because while plants don't use most of the sunlight that hits their area, they don't use so little of it that you can stack layers of growth dozens high. And skyscrapers are way more expensive per square foot than normal buildings, which are vastly more expensive than cheap greenhouses, which are much more expensive than just normal land. But someone inevitably points out that you could light your skyscraper or vertical farms, especially with modern super efficient LEDs. That's true, except the energy needed for that is hugely expensive compared to other routes of getting more calories per energy and effort put in. Of course, if you've got cheap fusion, that's no longer true and takes us to our next point. When we talk about vertical farming, or or growing food hydroponically on space stations or spaceships, we need to know how much energy it takes to produce a calorie, actually a kilocalorie, of human edible food, or for simplicity's sake, the amount of food one person needs for 1 year. Now that's a bit tricky to estimate with great accuracy, so I will be using very rounded numbers in the name of simplicity rather than high accuracy. That said, let's start with very old school cases. Back in our hunter-gatherer days, it took roughly 1 square mile of land to feed one person. That's all powered by the sun. That works out to about 10 to the 16th joules of solar energy. Back in medieval times, a 20-acre farm could feed a family decently, and that's about 100 times more land efficient, in the vicinity of 10 to the 14th joules of energy per person per year. Fusion usually operates at about 1% of total mass conversion, the E equals mc squared thingy, which is about 10 to the 17 joules per kilogram for total conversion, or about 10 to the 15th for fusion conversion. Meaning, for hunter-gatherers, you need about 10 kilograms of fusion fuel a year per person for all that sunlight, and for pre-industrial culture is more like a tenth of a kilogram, something akin to a shot glass full. At this scale, any other power concerns are totally dwarfed because while the average US citizen uses a few 100 billion joules of energy a year to run all that stuff, the equivalent of a couple thousand gallons of gas, that's less than 1 gram of fusion fuel. What about modern agriculture, or hydroponics? What about tailored lights by LEDs to use only the minimum amount of energy? Plants mostly use red light and don't use more than a small fraction of noontime sunlight. It's hard to be too precise, but if you really trim it down, you'll find you need a space only about the size of a living room or large bedroom stacked a few layers high with plant trays, using up maybe 10 kilowatts of power to feed one person. And you can even go a bit lower, down to just a few kilowatts, but 10 kilowatt figure is about on par with your energy consumption for other things working out to a few 100 billion joules a year. But we also like to have meat and some other stuff like green lawns or shared parks, so I usually put that annual human power consumption at a nice rounded figure of about 1 trillion joules a year, or 1 gram of fusion fuel. Incidentally, I keep calling it fusion fuel because we still don't know what we can use. Plain old vanilla hydrogen would be ideal, as the most common substance in the universe, but our focus now is in research on various isotopes of hydrogen and helium, like deuterium, which is still insanely common, but nowhere near as abundant as plain old vanilla hydrogen. They fuse easier, though. You gotta walk before you run. But what this means is, regardless of your fusion fuel, 1 gram a year ought to keep a person quite comfortable even on a deep space habitat so far from the sun it just looks like any star in the sky. 1 kilogram of that fuel would keep a man in very luxurious comfort for his whole natural life. And 10 tons of that fuel would keep a place like Yosemite National Park naturally sunlit for a year. So you could build some large rotating habitat with a fake sun as a wildlife preserve, running for nearly a decade on what some semi-tractor trailer or the space shuttle could bring in one trip. Yosemite is comparable in size to your average US county, with its average 100,000 citizens, or to a large O'Neill cylinder. Those being closed environments where you have all the power you want to recycle raw materials, just some supertanker-sized fuel carrier inbound from Jupiter, which is nothing but fusion fuel, would bring in enough to run a place for thousands of years. Remember that, because we'll reference it more in future videos. 1 measly kilogram of the most abundant material in the universe will keep a person in a luxurious lifestyle for a natural lifetime with plenty of room to spare. So that's what we're talking about when we talk about the real impact of fusion power and why it's so desirable. It's not about your electricity bill dropping while our reliance on finite supplies of fossil fuels and the problems associated with them goes away. It's about a total paradigm shift in terms of the scarcity of resources and the maximum population you can comfortably support, and this is a shift that's even bigger than the invention of the bow and arrow, and early agriculture, and the Green Revolution, all wrapped up into one. So that's it for today. Next time we'll be talking about rogue planets like we were supposed to be doing today, and you'll know why I seem to think something like that not only can, but would be desirable to colonize. Then we'll move on to reviewing rotating habitats in more detail. After that, we'll finally leap into interstellar colonization, and why so many of the assumptions about that which we have change when we think of them in the context of a fusion-based economy. In the meantime, if you haven't already seen them, try out some of the other videos and playlists on the channel, and if you enjoyed this video, hit the like button and hit the subscribe button if you want an alert when new videos come out. As always, thanks for watching and have a great day.